Welcome everyone. This is the 6th chapter of the Crystal Clear Electronics video series. We will introduce you to the world of linear power supplies and diodes in 5 shorter videos. The chapter was written by Balázs Ancsa and revised by Gergely Lagler and Gábor Proksa. Our presenter today is Ambrus Zelei. Welcome and please introduce yourself.
Thank you for the introduction. I was a teacher and researcher at the Budapest University of Technology for about 15 years in the field of mechanical engineering, including Newtonian mechanics. Currently, I work at the Széchenyi István University in Győr, where I am responsible for vehicle development. This basically means checking the properties of vehicles by simulation, and in most cases still at design stage. Crystal clear electronics is new to me, but I graduated as a mechatronics technician in high school, where the electronics and electrical engineering education was so thorough that I still remember the principles well. I almost became an electrical engineer, but there was also a lot of electricity in mechanical engineering. I'm very happy and honored to be part of the Crystal Clear Electronics project. For the linear power supplies and diodes videos, Daniel Pivko will be my partner. Please say a few words about yourself.
Thank you very much. I am currently a 4th-year student at the Budapest University of Technology and Economics that you mentioned earlier. Let's get started and see what a power supply does.
Okay, thank you. First, let's focus on powering our electrical devices. We hardly notice it in our everyday lives, but most of the devices we use require some kind of energy supply. A bicycle, for example, is powered by human energy. Older cars convert the energy from the petrol they are filled with into kinetic energy, and newer cars run on electricity, just like many other devices such as an iron, washing machine, computer, TV remote control, or even a mobile phone. Energy can be provided in many ways. For example, a TV remote control can be powered by disposable or rechargeable batteries. The phone has a battery. Inside the remote control and the phone there is also a power supply. That's what we'll be looking at today, and this ensures that the circuits receive the same voltage level even when the battery or the accumulator is half discharged.
And what about chargers, like the ones we use to charge our phones? Do they fall into this category?
This is exactly where they belong. You also need a power supply to charge the phone's battery. But there are many different power sources. You can charge your phone from a 230 volt AC mains supply, from a 5 volt USB outlet on your computer, from a 12 volt DC cigarette lighter in your car, or even from a solar panel. The phone is not designed to charge from so many different inputs. It is the power supply that is responsible for providing the voltage needed for charging in a given situation. So, depending on how I want to charge my phone, I need a different charger or power supply.
So, how can we briefly summarize the definition of power supplies?
Thank you for your question. A power supply, also known as supply, is a device that converts electrical energy from an input into an output that is suitable for the device you want to connect to it. It usually tries to maintain this output voltage regardless of what device is connected to the output.
So then, power supplies allow us to power our devices from several different sources. For example, a power supply can have an input of 230 volts AC, while its output is 5 volts DC.
Exactly. And we've prepared a little demonstration. Danny, please show us our tool. We may find ourselves in a situation where our device, which is now a laser level, is battery powered, but unfortunately the batteries are running out. Here we can calculate that these 3 1.4 volt batteries will provide a total of 4.5 volts while they are still charged. Later, this can be reduced to as little as 3 volts, so from this we can deduce that if we take this power supply that you see in the written material and set its output voltage between 4 and 4.5 volts and connect it to your laser leveling device, it will work perfectly, and you've gotten around the problem by getting the 4 volts from the power supply rather than from the batteries. And this example demonstrates very well that you took the input of the power supply from 230 volts, right? So you plugged one end into the outlet and the other end is connected to our laser leveling device.
You've seen that for each device, you must select the appropriate power supply according to its internal design. For this, we have to know the power supply's properties as well, not just the properties of the device.
Exactly. So, from what we have seen so far, the power supply has an input, 230 volts in our case, which receives the energy, and it has an output, 4.5 volts here, which transmits this electrical energy to the device connected to it. The output of the power supply is, of course, the input for the device connected to the power supply.
Knowing the definition of power supplies, can we talk about their important properties?
Yes. Let's see what the most important features of power supplies are. The main properties of the power supply are the parameters of its output and input, as well as the efficiency.
Out of these three things, the output is probably the most interesting at first, as it is the input for the device connected to the power supply. It is also exciting that the power supply tries to maintain the output voltage regardless of the device connected to it.
Yes. Let's start with the power supply output. Here we'll try some working circuits, as you can see here on the breadboard, and don't be scared at first, we'll build it up in easy steps and explain step by step why all these parts are here and what they are for. Most power supplies produce a specified voltage, but there are power supplies whose output voltage can be set to different levels. These are the typical laboratory power supplies. You can see two of them here, or the one we've just seen. Here, we'll just show you a couple of things. This is a dual channel power supply, which means that there are two outputs, and I can adjust the voltage and current limit on the two outputs independently. Similar to this, most power supplies can control their output voltage. This means that because of the controlling, the supply's output voltage level will be constant, no matter how the current changes on its output. Take the car's cigarette lighter as an example, which produces 5 volts out of 12 volt voltage, as you can see on the diagram. The voltage level stays at 5 volts, even if our phone is not connected to it. In this case, there is no current consumption, so the output current of the power supply is 0 amps, and the voltage level of the output is also 5 volts if we charge our phone, which consumes 1 amps current, for example.
I understand that regulating the output voltage means that the output voltage remains constant regardless of the load. But it would be interesting to see what happens when the output is not controlled.
It would be very exciting, and it's also our first step in the project. It's best to look at how a simple resistor divider, also known as a voltage divider, works. As the name suggests, the device is designed to deliver only a certain fraction of the input voltage to the output. This is the part that we will now need. On the diagram, you can see a photo and the wiring diagram of the device we are going to build. So now let's measure the voltage at the output of the resistor divider, i.e. between the two legs of the 680 ohm resistor. Remember what we have learned about voltage measurement in the previous chapters. If we've worked well, we should theoretically measure a voltage of around 4.8 volts. Let's also measure the current flowing through the resistors. This should be around 7.1 milliamps.
How did we calculate these? Can we summarize for the viewers?
Yes, we calculated everything using Ohm's law. You can see from the formula that the current is calculated by dividing the input voltage by the total sum of the two resistors, R1 plus R2, so 12 volts divided by 1 kilo ohm plus 680 ohms for a total of 1680 ohms. This gives 7.14 milliamps. This is a theoretical value, which is the current that will flow through both resistors. The voltage across resistor R2 can also be calculated using Ohm's law. Knowing the current, we can determine that the output voltage, the current, which flows through both resistors, multiplied by the resistance value of R2, which is 7.14 milliamps, so just what we got, multiplied by 680 ohms, the value of the output resistor, we get 4.86 volts, which is the voltage that will appear on the output.
So, from an input voltage of 12 volts, the circuit should produce 4.86 volts. Why do we get such a strange number?
Very good and very important question. Our real goal was to produce around 5 volts, but we're not quite there. But it's important to know that we can't buy resistors of any value that we would have needed. The resistor manufacturers would not be able to produce an infinite variety of values, so they mainly make values which you can easily combine to get the desired value.
Így főleg olyan értékűeket készítenek, amikből azért mégis egyszerűen elő lehet állítani a legtöbb kívánt értéket.
Most manufacturers use this so-called E12 series. This means that there are 12 values between 1 and 10.
És a 10 ohmos érték között, vagy hát igazából úgy mondanám az 1 és a 10 között, azaz az 1 ohm és a 10 ohm között például.
That is, typical resistor values between 1 ohm and 10 ohm are 1, 1.2, 1.5, 1.8, 2.2, 2.7, 3.3, 3.9, 4.7, 5.6, 6.8, and 8.2 ohms. And then you can multiply these by different powers of 10, so you can buy 68 and 82 ohm resistors, for example, or 680 and 820 kilo ohm resistors. And if we had the patience, we could combine these resistors so that the output of our power supply would generate exactly 5 volts.
So, I think I'm going to measure the actual voltage at the output. In this case, I'm measuring it at 4.93 volts. Why is this minimally different from the calculated value?
Well, yes, that's again a very interesting question. We were going to do 5 volts, we found out we were doing 4.86 volts with these resistors, and that again gave us a different value. Well, there are several reasons for this. For one thing, the value of the resistors is not exact. Their actual value is usually within plus or minus 5% of their nominal value. Secondly, the accuracy of our measuring instrument, the digital multimeter, is not perfect. The instrument manufacturer only guarantees that you will measure within a few percent of what the true voltage is. If we measure a value about 7.15 volts, then we missed something at the wiring. If it happens so, examine the circuit. That would simply mean that we swapped the two resistors, but the 4.93 volts you measured is perfectly fine, and fortunately, the inaccuracies made the true value closer to the 5 volts we wanted. And one can make a mistake, so if we measure this 7.15, it means that the two resistors are swapped. Well, that can always happen, even if you do your job as accurately as possible.
So you mean errors like connecting too much voltage to the input?
Exactly. We will talk about this later on. Now let's try our 5 volt resistor divider shown again in the diagram. A great test would be to connect an LED to the output and see if it lights up. The LED can be safely operated from just this voltage of around 5 volts, but by connecting a 330 ohm resistor in series with it. Let's see what happens.
I will now connect this resistor and LED to the output. Simply the 330 ohms resistor and the LED on the output.
First of all, you have to pay attention to the wiring of the LEDs, so it's no coincidence that you put them in the way you did, but we'll talk about that a little later. Well then, I see that our circuit works.
Yes, but usually the LED is brighter if I remember correctly.
Yeah, you got me. Well said. Actually, what is happening here is that our output voltage is not as high as it should be, so we just found out what it means that the output of our power supply is not regulated and why regulation is necessary. Let's measure the voltage again at the same point between the 2 points, that is our supply voltage at the output of the resistor divider.
I am measuring this at 3.28 volts.
Yeah, so we get this value of around 3.3 volts instead of the theoretical value of 4.86 volts. So what's happened is that we have loaded the resistor divider with the diode and the resistor, and that has caused the output voltage to drop. So our resistor divider is not capable of any regulation. Inside the power supplies, resistive dividers are not used for the conversion. For this purpose, the values of the resistors inside had to be changed continuously depending on the load.
I think we have learned a lot about the basics of how power supplies work. We're going to say goodbye for a while. This was the first part of the 6th chapter of the Crystal Clear Electronics curriculum. In the next video, we will review what happens at the input of a power supply.
Bye!
Bye!